this is a really good note to end this course on, and I'm really glad. Somebody asked me this question the other day when we were down at Karis Park with our trainer, and I've got this problem in this book I'm writing right now. I don't know if it's going to survive or not. I think it's a little too techy for most people. It's just right for this course, though. So the question is, go to Wikipedia and find the resource for embodied energy. List the embodied energy of several materials in the units of megajoules per kilogram. Energy per unit mass, which is similar to enthalpy, except it's like how much heat or chemistry or whatever had to be jammed in to make that thing. Find the entry for photovoltaic cells and convert megajoules per square meter into megajoules per cubic meter using 300 microns as a typical thickness. So I just pasted this thing. I'm going to see if I can find days to payback on my computer, because I know I've got it in a cell. If I can't, I think we can just bust it out in Excel pretty quickly. Type. Oh, look at that. Search engines are getting faster on these machines all the time. You used to be able to find something that quickly. Okay, so let's go through it. So let's go. We're in Wikipedia. You guys all paid your $3, right?
Oh, yeah.
It's unbelievable. It's huge. Okay. So megajoules per kilogram is the typical metric for embodied energy. They're also looking at how much CO2 gets cranked out every time one of these things gets made. It's funny, though. You go down here to PV cells, and it's different. It's given in megajoules per square meter. But as we all know from this course, the typical means of making, you're growing these giant crystals and then you're slicing them into little wafers. So and so I've got polycrystalline 4070. And my little problem, I just put it as 4,000. Now, this is critical, and we've been over it a million times in 101, 102, but it's critical for any engineering analysis. Always put your units on there. Megajoules per square meter. And then over here, it's just a number. I put in 4,000. We can type in 4070. So that's what we just saw for polycrystalline on the website. Now, layers, or thickness, I put on 300 microns. So if you stack 3 or 4 of the hairs on your head on top of each other, that's about how thin these things are. We're soldering them together several years ago. It's just like soldering Pringles potato chips. They're just super fragile. But now we've got the thickness. We can figure out how many layers there are in a meter. I'm just using a cubic meter, so I just said per, probably more correct just to say layers per meter. Doesn't change the answer. And for this, I just took 1 million, because there are 1 million microns in 1 meter. So if the layers were 1 micron thick, there'd be 1 million of them. But they're 300 microns thick, so there are 3,000. So if you've got a meter here, you could have 3,300 little solar cells between your hands. Seems like a lot, but that's the reality. Maybe it's a little more, maybe a little bit less, but you can play with the numbers. Okay, now we want to know the embodied energy per cubic meters in solar cells. Well, there are 4,070 megajoules in a square meter, and we just took that square meter and stretched it up into a cubic meter. So now we're looking at 13 terajoules. It's a lot of juice.
For 3,300 cells?
For a cubic meter of cells requires 13 so this was megajoules, gigajoules. It's more than you think. 13 terajoules to make a cubic meter of PV grade doped silicon. Well, start to finish. Now, let's just see. So let's just see what's sort of the highest. So they are some of the other, like polystyrene. Ooh, 88. Sorry, we're almost 6 orders of magnitude greater.
Yeah.
So if you put PV cells on the same line, everyone's going, oh my God, why even bother?
Way better.
Yeah, make plastic instead, right? Not saying don't use polystyrene to insulate your house, but so there's that number, large. This cubic meters per square meter doesn't really matter. Now we want to figure out how long does it take to make that much energy. And so I just started with Missoula here, and I said 4.4 kilowatt hours per square meter per day. I converted that to megajoules per square meter per day by multiplying by 3.6. Yeah. And here, days to pay back, megajoules per square meter. Oh, I kind of just did it the kind of the quick and dirty way. Yeah, I didn't end up really using this number. It looks like, but I just took if it takes 4,070 megajoules to make a square meter of solar panel. I've got my megajoules per square meter per day, divide the two, and it's only 257 days till payback. It's less than I thought. 8.6 months, or less than a year, 70% of a year. I thought it was closer to 2.5, but. And if you were to look at, so that's the energy payback. You know, we just spent the previous half hour looking at the financial payback. The other kind of weird stuff that I think is coming down the pike, and this is the debate, is what is the true payback of keeping CO2 out of the atmosphere? Because if it means that we don't lose Florida and Wall Street, it's a pretty good payback to keep that real estate as part of
It's almost undefined.
North America. I
You
know.
can't figure out.
So somehow you're like, yeah, because at some point, the money and the energy collide, and it starts colliding when you have to preserve vulnerable, valuable real estate.
Another tough thing, I've been kind of working on an embodied energy model for the blue sky stewardship guys.
Yeah.
And the tough thing is you can basically like chase it down the rabbit hole.
Oh yeah.
You can ultimately say, so there's also, a crew of workers who have to drive to work to put the panels on your house and
Right.
set them up, make sure they work
Right.
in order for them to even produce energy.
Right.
That's another cost.
Mm-hmm.
And then, like basically you can trace it all the way back to the photons
Yeah.
in the sun that like initially provided the energy.
The food to feed the workers, to make the
Yeah.
carbon bonds and the
It's-
yeah.
You have to pick a spot.
Yeah.
This is where we're done.
Yeah.
This is.
Well, and that's why I like going back to that, going back to the Uncle Helios problem that I call it, where you've got the 10 million to 1 payback ratio, where we're currently burning fossil fuels 10 million times faster than they were manufactured initially. Yeah. It's not, it's not necessarily a bad thing. It's just whether or not the entropy accumulation in the atmosphere comes back to bite us or not. There's always somebody inventing something cool every day. So, all right. Well, guys, thanks for being here. I wish I could have done a little more thorough job teaching this course. It's just been a little bit of a rough ride this semester with the lack of adjunct support. But I did record a YouTube video earlier. Matt Byrne was in my office, and we will be able to offer as many courses as we need to in upcoming years. It's just that the admin is just sort of repackaging or rebranding energy tech under pre-engineering on main campus and the green building on west campus. Like the courses, not every single course will be there exactly, but they'll just sort of come back as the student population comes back. But that said, like if you want to take 242 solar thermal in the fall, let me know and we can just offer it under 291 or 290 or 292. So.
Is it possible to do energy storage and distribution in the fall?
Energy storage and distribution relies a lot on the motors course 213. So we're going to offer 213 in the fall, and I've already advised a lot of students and already told physics that we're going to do 214 in the spring. So I think we're going to just stick with that plan. I tried it once and it doesn't do anybody favors. The quality of the teaching goes down, and it's better. So 213 will be in the fall and 214 in the spring.
Right.
Yeah. Thanks for asking that. Okay, that's a wrap. Unless there's any other questions at all? ABSIP's launching. I'll finish grading. Yeah.